Alright, in this video I'm going to show you how to solve the heat equation. So let's get started. And then a blue title box, just like that. And then before we write down our general form, in the question statement, you should be able to figure out what the value of K and L is. So that should be pretty easy. So K is whatever the constant that exists in your differential equation, and the L is the length of the rod. Is usually one-dimensional. So you should be able to find those two variables easily. So the general expression for the heat equation is UT equals to K. So this K is the same as the K right there, UXX. So we're going to use the method of separation of variables to turn that into a form like this. You'll see. So because on the left hand side, it is u of t, so it's x of x times t to the first derivative equals to k doesn't change, and then uxx, that is x to the second derivative times t, and then we're going to rearrange that just a little bit again, and that we will have x double prime of x equals to t prime over kt again. K always stays with the t term, not the x term, equals to negative lambda. This is a shortcut. I'm just going to tell you straight that it is kind of lengthy to explain, but when you're solving heat equation as well as the future wave equation, always set your lambda, always set this differential equation equals to negative lambda, and where lambda is greater than 0. So okay, let's move forward. So we're going to analyze this equation. First of all, we're going to analyze the x part. So let's write that down. X double prime over x equals to negative lambda. Rearrange that a little bit. We'll have x double prime plus lambda x equals to 0. R square plus lambda equals to 0. This is our characteristic equation, and then that will give us r equals to positive or negative lambda I. All right, so now we can write our x solution. So x, this is a big X, equals to c1 cosine square root of lambda x. This is a small x, and then plus c2 sine square root of lambda x. So we're going to differentiate it just for fun. I mean, not really just for fun, but because we're going to use it sometimes. So I'm just going to demonstrate how to do so. It's actually pretty easy, and you just do the regular differentiation steps that you do in calculus, and that will give us negative lambda c1 cosine. Oh, actually, cosine becomes sine. Cosine becomes negative sine lambda x plus square root of lambda c2 cosine square root of lambda x. Okay, so at this point, what you will do is apply boundary condition, so BC, boundary condition, and then find the value of lambda as well as xn. So lambda is in terms of n, so your x, once you plug in your lambda, your x will be expressed in terms of n, as well as x, of course. And then we're gonna draw some arrow lines since we finished our first part, and we're gonna go over here. We're gonna analyze the second part. T, so it's t prime over kt equals to negative lambda. That will give us t prime plus k lambda t equals to 0. Remember what we did. when we are reviewing our content. So we're going to solve this first order differential equation using the method of integrating factor. So I of t becomes e to the lambda t, and then our t solution will become 1 over I t and then C2 plus C1. Everything, if you don't understand what this two terms means, go ahead and watch my review video, but the solution will become T equals to C3E negative K lambda T. So just so you know that I would like to color code my important stuff. So for example, I would like to color everything that is important in pink, everything related to X in green, and then everything related to time in blue. So just so you know, and then we're gonna differentiate it again just as we did in X for fun. So T prime equals to negative K lambda C3E to the power of negative K lambda T. So now we're going to do is we're going to formulate formulate our U. So formulate U of x t equals to the infinite series of n equals to 1 bn xn tn. So let me color code that again. Remember what we talked about when we were discussing the concept of solving partial differential equations? So this really comes to play because now we are expressing our solutions for our PDE as a infinite series. In this case, it will be a Fourier series. And I'll say, and I don't know if you remember a little bit, I said one way or the other. So this is the first way. So we're going to use the remaining boundary condition to find Bn and n if possible. And then the second way to do it is that I'm just gonna go ahead and tell you the general form of the solution, which is U x t equals to infinite series of Bn sine m pi x over L. This all should be in green because this is the x term, and then the t term will be e to the negative k n square pi square over L square t. So this is L. And where the value of Bn equals to 2 over L. So this is a Fourier sine series, so 0 over L, the fx, the original boundary, one of the boundary conditions, and then sine m pi x over L dx. So this is the basic concept of solving heat equation. So let's dig in a little deeper and talk about two specific cases. So the first case is heat equation with 0 temperature on both ends. So heat equation with 0 temperature ends. So let's draw another title box right here. Let's move it to the center, and then so the basic solving process is the same as we discussed above, but the boundary conditions, which we did not specify in here, will be u 0 t equals to 0, u l t equals to 0, and then the other boundary condition is u x t, 0 equals to fx. So what this boundary condition means is that u of 0 t equals to 0. That means, let's say if I have a rod here, that this is my 0 and this is my L. So we're gonna so on the left side, my temperature will always remains to be 0, and then on the right hand side, which is this case, that no matter how the time changes, that my temperature at x equals to L will always be 0. And then there is and then this boundary condition is the initial heat profile. So at the initial time, so at t equals to 0, maybe I will have a heat temperature profile like this. So, and then now we're going to solve this. So because that u of t equals to 0, that means so we are going to, because t is freely changeable, and then we are more concerned about the x term here. So what this two boundary condition will tell us is that x of 0 equals to 0. So that's what this boundary condition tells us. So that will lead us to what is it? So you can see that if we let x equals to 0, sine of 0 becomes 0, and then cosine of 0 equals to 1. So x will become c1, but c1 has to be 0, so c1 equals to 0, right? So that will leave us to the answer of x, and that is x equals to c2 sine square root of lambda x. So the c1 term gets canceled out, and then let's use the second boundary condition, and that is x over L equals to 0. So because again, the time variable we cannot really control, but what we can control is the x at L. So x over s at L equals to 0. That tells us sine of lambda L equals to 0. So actually, let me backtrack a little bit. So this is our expression of x landed with, and then x at L equals to 0. So we have two options. So first we can let c2 equals to 0, but what you realize is that when c1 equals 0, c2 equals to 0, x will equal to 0. So this is an trivial solutions that we're not really interested in. So we cannot let c2 equal 0. The other option, what we left is we let sine of square root of lambda x equals to 0. So this is what we did here. So in order to make this sine term equals to 0, that means square root of lambda L has equals to m pi, because let's draw a coordinate right here, that in order to let sine of n L equals 0, it has to be negative pi or 0, so that is just m pi. So what we'll find is that the square root of lambda equals to m pi over L. So we're just rearranging that, and then the value of lambda equals to n square pi square over L square. Okay, so this is it. And then let's solve the the T part then. And so T prime plus K lambda T equals to 0. This is, we just done this before. It is literally right here, the solution. So that will give us T equals to C3 E negative K lambda T. So let's formulate our solutions. Therefore, U of xt equals to the infinite series of n equals to 1, bn, xn, and tn that equals to infinite series of n equals to 1, bn sine n pi over L times x, and then e to the negative k n square pi square and L square, and then t. So, but we're not done yet. We still don't know what the bn is. And by the way, in case you wonder what the constant terms are why they are gone in our final expression, and that is because C2 and C3 has been absorbed by the bn term. So last boundary condition, which is this one that we have not used. So last BC. So this BC tells us that when t equals to 0, our boundary condition will be equals to fx. So let's set our solutions that we generated right here. Let x equals to x and then t equals to 0. So that will give us infinite series of n equals to 1, bn sine n pi L over L times x. And then this term, because t is 0, e to the 0 power, that will just give us 1. So, and that equals to our initial heat profile, and that is Fx. So everything should be crystal clear for you right now. So what we need to do now is just to solve for Bn and the n, so the range of n values that you can use in this final solutions. Then you just go ahead and plug these two values into the solutions right here, and there is this is it. And this is how you solve heat equation with 0 temperature ends. And I forgot to tell you that in this question you also need to know what the value of K and then L is. So, all right, let's talk about the second case, and that is heat equation with insulated ends. So, heat equation with with insulated ends. Title box, here we go. All right, so the boundary condition that we are given in this insulated case is a little bit different, and that is u x 0 and t equals 0, and then u of x at L t equals to 0. And then we also given the initial heat profile, and that is u x 0 at x fx. So the physical meaning of this new boundary condition is that, let's say I have a rod right here. Instead of temperature at equals to 0 and then L, it doesn't have to be. So but instead, heat cannot escape. So let's draw an imaginary boundary right here, and then my heat cannot travel through this boundary. It is insulated, and then we can have an initial heat profile that looks like this, or like this, whatever we want, just for fun. So, all right, let's go ahead and solve it. Because now we're given a derivative of u. So remember the cool fun thing that we did to differentiate that x. This becomes very important now, because when x prime equals to 0, x prime at 0 equals to 0, this is our first boundary condition. Our C1 becomes 0 because sine was 0 equals 0. So C1 doesn't really matter, but C2 matters now, because cosine of 0 equals to 1. So x prime at 0 equals to C2. So that means C2 has to be 0. And then, so that will give us x equals to C1 cosine square root of lambda x. And then we differentiate that just to show you. X prime equals to negative square root of lambda C1 sine square root of lambda x. So let's use a second boundary condition, which is right here. So that means x prime at L equals to 0. What does that mean? We can't, so again, C2 is now 0, so we cannot let C1 0. So we have to let sine square root of lambda L equals to 0. So now, hold on, let me just let's think this through. So square root of lambda L equals to m pi, because again, how can we let the sine become 0? So that has to be equals to m pi. So square root of lambda equals to m pi over L, just same as before, and then lambda equals to n squared pi squared over L squared. And this is it. So you can see that from the 0 temperature end case, we have a sine term, but in our insulated case, we have a cosine term. And then what you realize is that even though if it becomes an insulated case, our differential equation for the t term does not change. So let's just go ahead and write that down really quickly. So our differential equation for time is still the same, which is t prime equals to t prime plus k lambda t equals to 0. So that will leave us to the same solution. T equals to c3 e negative k lambda t. So our un, so now our solution becomes u x t equals to infinite series of bn xn tn, and that equals to infinite series of bn cosine m pi over L times x times e to the negative k n squared pi squared over L squared t. And there you have it. Now, again, we still have one more boundary condition to solve for, so let's do that. Last boundary condition. So let's let x equals to x, t equals to 0. So at u of x and then 0. So that will give us infinite series of of Bn cosine m pi over L x. Again, that the e term, because of t equals to 0, that the e of 0 has to equal to 1. So times 1 equals to our fx, initial heat profile. Then, again, solve for Bn and n, and then plug that into your solutions that we generate from here. And then this is how you solve heat equation with insulated ends. So this is it. This is an overview about how to use the method of separation of variables to solve heat equation, along with some special cases that, zero temperature ends, insulated ends, showing you the process of solving them as a whole, instead of going through a specific case, a very, very detailed example question. So in the next video, we are going to talk about the wave equation. So once you understand the content right here, you should be ready to move on. So I'll see you in the next video.